equations. Most complicated and steady compressible Navier equations. They have other three types of characteristics. And for step one, without temporal derivatives, it has the characters of elliptic and hyperbolic. Without the considering of visit in all equations, is pure. For steady one, it's pure hyperbolic. And for steady one, it depends on the flow speed. For supersonic flow with a number larger than is pure hyperbolic. But for sonic, it has be elliptic. For transonic, it has both the characters of hyperbolic and elliptic. This is why nonlinear discontinuity are basic structures in compressible flow. Comparison is there in compressible Navier equation. There's no hyperbolic feature, no matter in steady or step one. Then how nonlinear discontinuity shock waves? For example, consider a scalar nonlinear convection equation. The information of phi is transported with the speed of u, which is the value locally. Then if u is not a constant spatial, two cases appear. First is the equation is compressed with the convergence of the terrestrial line. All they are expanded their divergence of their characteristic lines. Then the shock wave will appear and the characteristic lines merge together. So nonlinear discontinuity always have the feature of compression and convergence. This is an important point in this work. We can also distinguish nonlinear and linear discontinuity in the same convection equation. For waves, UL is less than UR, and all differ from the speed of the shock space. But for linear discontinuity, the speed of UL equal to UR and equal to the speed of the discontinuity. So in a hyperbolic system, the linear discontinuity never appears or mentioned. All we need to do to trick it sharply. For example, interface between two material or the surface of one material. If only inside of one material, it also exists near discontinuity. We call the contact fields. And it moves with local velocity. We also named material discontinuity. They are all same things. We have introduced that unsteady Euler equation, the pure hyperbolic equation, it has no visit. So always use the equation to study the numerical sense of compressible flows. In fact, it may be hard to solve the Navier equation for its pure hyperbolic feature. In this work, we see the convective form of the action equation following the work in 2019. But the structure is a little different. We built a relation from SYT to the convective variable, not directly to the convective variable. Because we build the neural network to solve consecutive variables, then we have a density denominator. And the simulation may not variable, but this is only a small trick. In fact, for this work, I changed the convective form of PD to non-conservative form in pins. No, in traditional conservative form is better, no matter in theoretically practical. It can keep back the conservation of conservative quantities if we use integration scheme, for example, finite volume or finite element. But to pin is different. We have tested no matter you non-conservative form or conservative way, the result has little difference. But use conservative form is cheaper because it only needs to for derivative. But with conservative form, we need to solve 12 derivatives. Next, I will compare pin with traditional method and talk about my understanding of pins in solving compressible flow. Traditional methods such as fit difference finite volume method, they build scale locally in space and time, so can be said from locality to global method. And pin change the problem into a global constraint optimization problem in time and domain based on the powerful expressibility of network. So people care about the globally first. It's difficult to say strategies here, but globally really bring many benefits to pins. For example, there is no need of local information. Then we do not match as other residual ones are independent logically. We are free of games. It's easy to reduce constraints to the rules matter from data, for example, inverse problem, or from physical properties. And I think there are other benefits that are introduced by the neural network. For example, in the crystal dimensionality and compression of data easy to use. I will show example of this later. But pins of local information may bring troubles. Then I will how pins encounter trouble in including shockwave. We have introduced the basic property of shocks, and we can simply understand their form as a compression of nearby regions. So at first, it is shockwave may formed. A simple example of shock, the progressive motion case. The initial is smooth the sine wave, then it will be compressed to discontinuity, and velocity is u itself. The left is positive and the right part is negative. We first show the simulation by original pins. It takes about 15,000 with BFGS optimizer. We first look into a load tree. At first, 1,000 step, those descends quickly. However, after that, we can know descends, and most of the loads PD load. We give you predict by neural network at different pokes. And near we get far away from the exact solution. And the loss function cannot really indicate the error of the solution anymore. Also, we get the residual distribution in this. We can see most of the residual is located on the points inside the discontinuity regions. We name them as the transition points. This component does not size us at all because in traditional method, transition points in discontinuous regions also carry more errors than smooth points. Then we can review how traditional method capture shocks. There are really many kinds of capture methods, but basically they adopt strategies. First, introducing artificial velocity or scheme velocity into discrete portions. to avoid gradient in solution. But this is not enough. If our spatial scheme is one order, we need to reduce its order to prevent numerical oscillations. So in traditional method, we can only have low order in transitions, but we still can keep high order in smooth regions. This is because due to the equation nature of a hyperbolic and the local quality of traditional method, the error in the transition region will not influence the solution far enough from the discontinuity. But strategy networking pin, we can think this is that we let all the residual on transitions as L1. Another regions are L2. And source L1 with other with the 0.1, and L2 is less than L1. Then LPDE is with the same order of L1. This means theoretically the training is lose the control smooth regions if we can decrease L1 further. Because the final gate is PDE. So if we want to capture shocks with viscosity, we first need to ensure the conversion in transition points. Then the solution is smooth enough. All the loss in transition points will still dominate total loss. At last, we can assert in capturing PSMA cannot surpass traditional method if we use same strategy. It seems that we are stuck currently. However, we can consider an extreme case that pins can remove all the transitions. What will happen? This situation is hard to imagine because it will not happen in traditional method. First, L is disappear. Even time gradient will introduce errors in strong or PD, but there is no importance. So all loads are from smooth regions. We can train smooth regions. Then pin can convert to acute regions. Here we have a question. Can pin remove all the transition points and express continuity? Here we first show linear discontinuity case that is used in text capture scheme. We can use it to pin in built-in linear discontinuity. Just with the original pin, we can get a back result that may be better than many structure methods with the same number of points. But to pin linear and non-linear discontinuity very different. With this case, just to illustrate that pin can express gradient discontinuity. But ones cannot fully express strong nonlinear continuity. We found that there is a paradoxical state exists on transition points. Then I will explain it with their bogus portions. Based on Bogus analysis, we know that transition points carry most of the equation residuals. Then neural network puts most of its attention on training them automatically. However, transition rate cannot be controlled by their strong or PD. Then if we get this form or use some epoch, neural network may try to raise the gradient of transition points and get this and increase gradient of transition points. Will let the solution approach to exact solution. But because of this reason, the transition point cannot be controlled by the PD directly. So we increase gradient of the transition point. We also increase the residuals of the transition point. Like this, neural network will treat at one direction. Then neural network may try a different direction that creates decreasing gradient. But decreasing gradient like a solution away from the exact solution. So even on each transition point, the residual is reduced, but more transition points are produced in, and the totals also can be effectively reduced. Symmetry increasing or decreasing the gradient of transition point, the totals cannot be effectively reduced. So we call this status paradoxical status. In fact, it's very easy to understand it happened. The midpoint between linear and non-linear discontinuity, the physical compression process as we introduced. PIN will simulate physical compression process, so it will try to increase the gradient of transition points. But no matter pins or traditional method, gradient will also have error and residual. This is the basic mathematic mechanism. So the confirmation that pin struggle. To the confrontation, we propose a new theory. Weakening the attention of neural network transition points. This seems very counterintuitive, as we know many other problems. When pins are under performance, we usually try to straight in hard training. Then we need to wait on transition points. Can imagine if we weaken the attention on transition points unnecessarily, pins will focus on training a smooth region, then depends on the physical compression on the left and right smooth regions. The transition region will be compressed without the rotation. At the gradient on the transition point will not influence the training, just like passive particles. And they will be compressed out the transition into smooth regions. Then we will get strong discontinuity without transitions. And also we can get an accurate smooth region. As this is the basic idea of this, so I represent it with the picture. As pins are good at smooth regions, we put our attention on regions, ignore transition points. If we can get a accurate smooth region and their physical correction from smooth regions, we can also get a strong continuity without transitions as they are all compressed in smooth region. Based on that, here we have two questions following. First is detect transition region of nonlinear discontinuities. Second is how to adjust the attention neural network. For the first detecting, there are huge numbers of detectors if you invest it. Recently, some researchers had to use a driven deep neural network to detect them. In a classical framework, we have two strategies. First is the field detector that usually used in early age, but not all of them are structured on mathematically relations. We think use physical lines suitable because we lack of we inspiration from the study of artificial velocity, for example, in the work of Newman and Rickman. They do the first dynamical simulation of compression flows. They use the divergence of velocity to detect and strong compression regions. Remember that in compression natural equation, this term is always oppositely if the is positive, the flow field is expansion, and if it is negative, the field is compression. Then another problem is how does the tension insert pins automatically adjust the tension based on the residuals. We can actively adjust it. In fact, is widely used neural network, for example, in natural system. The work of Kalani and Braga introduced soft tension mechanism to pins in solving this problem. Knowledge there be two adjust tension in pins. The first is use widely to sample we can resample the residual points. Maybe all of us have it in pins. Another way, weighted residual points. As well, this is only in field work, including this one. If we want to strengthen the network in some region, and those strategies may be safer. And the weighting residual be weaker than just raising points, but it's also weaker. However, if we want to weakening it in some regions, for example, in transition regions we want, weight residual may be more so because reduced points in those regions will cause a low resolution of discontinuity. Based on above analysis, we introduced the weight equations method in PIS, and weight lambda is contrasted as following. When the region is compressed, lambda will raise, and in regions lambda always close to 1. Here epsilon is takes the point 0.1 is not very sensitive. Another good property of the weight is that it is definite. Compared to classical short capture method, they introduce viscosities and the equation property. Reducing of lambda will not influence solution of the equation circularly, and weight equation is equal to the original equation. Till here, I have introduced all the idea answered all this. Then we resolve the first problem with the weighted equation pin. You can effectively reduce the totals by about 2 hours, lower than the original results. Then we show result of with the training, the solution more accurate, and the transition points all compressed out instead in the center. Because this one is a fixed point that is velocity is with also we see a very expected result that the residual on the E1 transition point is also converged. And then with the weight lambda distribution base, we see the minimum is about 0.2 and it decreases with the compression. Then we had the generalization of method with all equal both one dimension and two-dimensional cases. First is problem. This problem is retesting pin, one-dimensional random problem with a running structure, a contact continuity, left running affection wheel. We first compare the result, solve original pin and pin same current get with August equation problem. New method can effectively converge the two loops with need to order than the original pins. We give the development variables at the end of the field time in different epochs. Organisms may struggle in the transition points. Well, with the weighted equations, pins can obtain a shock without decision points. Also, here we compare the result with the traditional order Wizzy method under a similar set. Figures that the difference with traditional capture method is we do not need to introduce viscosity to capture shocks, so we can get a sharper discontinuity without transition point, just like we designed. But in the method, local viscosity is necessary. Next is another one-dimensional Riemann problem with strong and strong contact with. We get the same result with the solved problem. Then we take a two-dimensional Riemann problem. We treat the problem with 100,000 points by Latin hyperloop sampling and up to 15 per dimension with the 100 times 100 uniform mesh. And compare it with Windows under same mesh. We can see the discontinuity is more sharp than by pins. Then we compare results of velocity pressure. We get similar illusion that the discontinuity of velocity is more than we can see. Also, we take an unfair compare. In this case, we use the same model last page, but test it under 400 times 400 meshes, and compare it with Windows same fan mesh. We can get a super convergent results. The discontinuity is as sharp as Windows, even the data is in huge gap. Then at last, we have a transonic two-dimensional case. The flow path cylinder, the setting of computation is met here. Here we have an interesting result. In pins, we passed our data into the network meter. So with the failure and 90 nodes each layer, we only need to store 100 numbers. But with the traditional method, even we take only one size in M, we need to store at least 100,000 numbers, even activate the information. We see the comparison. Here with the streamlines and density counter. On top, the pin can get similar flow structure as we know the pins can carry even the
Lilio, Can I ask you a question? Is this Euler or is this Navier-Stokes? Because I see vortices in the background, in the back. Why there are vortices if it's Euler?
Why the text is
Is this Euler
is
Euler or Navier-Stokes? This one.
This is Euler equation problem.
Oh, it cannot be Euler because you have vortices. So then maybe artificial viscosity. In the background, you have separation. You cannot have separation if it's not Euler, if you don't have. So it's maybe the artificial viscosity.
Let me think.
No need to think.
Even
no wake. No wake. There's no wake. There's no separation if there's no. But I think there's production of artificial viscosity that causes the separation. That causes the wake. Anyway, please continue.
Oh, thank you. I'll continue. Then with detailed comparison in here, we can see pink shock wheel sharp even with points, and other region we can see is significantly smoother than the Windows. As Windows introduced dynamical oscillations in this case, this is also a major disadvantage of other shorter method, that it cannot totally eliminate the oscillations. When we compare velocity, we can get very similar the smoother route in some region with Windows. At last, in Pin's way has following advantages in computing enhanced flows. First, it can capture shock wave and smooth computing regions, and suitable for conditional problems. We compress data into the natural parameters and it's to extract. We also have simulating other supersonic and transonic compression problems. Due to the time limit, I don't introduce them here. Then I give solution. Pins have many outstanding features, but have trouble in computing nonlinear discontinuities. We will that there may exist paradoxical features on transition points. So we propose here that weaken the tension of the network in different regions to break the confrontation. Then we can physical weight in governing equations. And Pin's way performs remarkable in solving one-dimensional to dimensional equation problems. Then I refer some latest work. Function is one of my partners try to propose a motoric framework of weighted residual pointer with trainable coefficients. Another partner of me, Hui Xie, used a similar idea in solving isotopic diffusion equations. Also, diffusion equation is smooth, but heat flux may discontinuity. He first used the heat flux from second order system into first order system. And then he introduced a distance decay weight function into the first order formulation, and the weight is decayed near the discontinuity. And he have proved that for discontinuity or discontinuous isotropy fusion problem, the base pin may for one more heat flux conservation error across the face. While the conservation error pins way is all where is the weight west. Here's here's a dynamical example. In this example, the different coefficient is discontinuity. With base pin, the absolutely is 1, and with the new method, we can lower absolute error. Then we introduce another work that is going. As we find that in solving linear discontinuity, pins are outstanding. Even just with the arranging pins, we can hold the square wave with low dissipation. So with pins may be suitable in treating interfaces. In the building of interfaces problem, there are two properties that are most important. First is low dissipation that we want sharp discontinuity. Another is conservation. For example, conservation of water in compressible flow, mass in compressible, and pins that the two facts as we introduce conservation constraint to the loss function. Then we use the situation pins solving a classical interfacing problem. Till now, back to our knowledge, there are other methods to get this sharp, the long tail after fail time with equivalent methods or point under a framework. I have listed 3 work here. You can find my work in the Git. Welcome comments and questions. I last thank you for your attention. It's all my presentation. Thank you.
Thank you, Leo.
Hailey, I have a question. When you for the scalar equation for Berger's, you have only one lambda, right? Because you only have one variable.
Right.
Yeah. When you go to the Euler system, do you have a lambda for every state? You have lambda for U, you have lambda for rho, you have lambda for E. You know what I mean? So when
I will.
Okay.
Yeah.
How many lambdas do you have? You have in the beginning when you introduce lambda as a weight, it depends on the divergence of U. For each state,
if
you go back,
we only use one lambda in this work.
But based on what? For Euler equations, what do you use for U? Do you use the velocity? You use the density? Yeah. Here, what is U is the vector.
This is the velocity.
You take the vector. I got it. Okay, so you take the so you have the whole vector. So the entire state. Okay.
The divergence of the velocity. Yeah.
Oh, the divergence of the velocity only. I see. But
yes, this is.
But see, then how can you? Let's see. You can have contact discontinuities and you can have shocks. So how, like in the Euler system?
This way only to detect shock waves, and for linear discontinuity, we have tested it. Even the original pins can capture it very sharply.
I see. So you're saying you don't do I got it. You don't do anything at the contact discontinuities, only for the shocks. Okay, got it.
Yes, yes. So we use pins in capture linear discontinuities in this work.
Yeah.
In this work, do not
got it.
we do not introduce the weight into this into pins.
Yeah, yeah. Another question I have.
Only use.
Yeah, I have one more question is on because you're using the non-conservative form, but how do you make sure that the shock will travel at the right speed? Because in non-conservative form, we don't guarantee that the speed of the shock is correct.
This is a very good question. In fact, in this work, we still use the conservative form of equations, like here. I just say in the following work, but in pins, even you use conservative form, you cannot keep the conservative characters. So in fact, this work only used to get a strong discontinuity, but we have tested that. I will show later. I will show later. We have when we compute supersonic flows such as solve problem, pins may fall into random non-physical results.
Right.
This is some cases. So we use weighted equations can let us quickly converge to a discontinuity result, but it cannot it may not be a physical result. We know in traditional method, many extra physical features are introduced, such as in Riemann solver or the spatial schemes. We know in solving Euler equations, only the PD cannot define the problem. For example, we need to introduce entropy conditions. But in pins, we do not introduce any physical constraints, so it will we will have physical results. So we may first sort of entropy conditions. It has many expressions, but in pins we think entropy condition is very weak equivalent constraint. It's only effective locally in game. So introducing in entropy condition, we have tested it not work in get a physical result. So in later work, we have introduced a local conservation relation that is a ranking homogeneous relation. With this relation, we can define the problem and get a physical result. Yes. So as pins is lose locality local property, this will have problems. So introduce more locality property maybe more suitable in for example in the Euler equation problem.
Yeah. Good. Very good work.
Thank you, Professor Kanidakis.
Fei Chen Hao.
I have
English
a
is
question.
very
Can I ask a question?
Ahmad, yeah, go ahead.
So this is Ahmad from Brown. So where you define your lambda, you scale your lambda with divergence of u, right? Your
Yes,
detector
the
function is,
lambda is with the velocity.
What's your question, Ahmad?
so
Hello.
the question is, in traditional shock capturing methods, the detector function is del dot u, and then they apply higher order derivative of del dot u, and that would improve the convergence rate. So have you like tried to scale your lambda with like second order derivative of your del dot u? I was just wondering how would that affect your pin solution? Like, would it converge faster to the actual solution, or maybe make it more oscillatory? Or that was my question. Have you tried that,
Okay.
scaling your lambda with like higher order derivative of del dot u?
Ahmad, maybe you can annotate.
Indicate-
Can you annotate on the screen?
So
Maybe see. Yeah, if you can annotate. If you can write, it will be better.
yeah, so let me see. So you have a detector function, let's call it FD, and yours is del dot u. What I'm saying, you can scale your lambda based on the derivative of FD with respect to your like second order derivative of FD with respect to the space. And when we do that in traditional method, we actually increase the convergence rate of the numerical method. Like if you use this in traditional numerical method and then calculate the convergence rate for a smooth problem, this will increase the convergence rate. So I was just wondering if you can scale your lambda with higher order derivative of del dot u, what would happen with pins? That was just my question.
You mean if I decay lambda?
Yeah, construct. So
at
the way that your lambda works here, so when you have shock waves, you get a big denominator, right? And then you are reducing the attention at shock waves. That's what you do, right?
yes, what I do. Yes.
So what I'm saying, if you can create same mechanisms, but with second order derivative of your del dot u, it's like finding like it increases the sensitivity of your detection with respect to shock waves if you use high order derivative, but at the same time it will add more oscillations to your solution. I was just wondering how that would work with pins.
You mean it enters the weight into a traditional FD method? Oh,
The same method in your pins, but scale your lambda with higher order derivative of del dot u. That was the question. But anyway, that's it's not I don't know.
We can try that, Ahmad. We can try it here.
Yeah.
It's,
can translate
Yeah.
me.
Yeah, it should be. Yeah.
it's amazing that it works so well. I
Yeah.
was impressed with beating the W is not easy.
Yeah, it's really impressive.
Because we couldn't get even the SOD problem. We couldn't solve the forward SOD problem like you saw. Only the inverse problem with Ameya and Mao. But he did an excellent job.
Thank you, Dr. Liu. Thanks for tuning in and thanks for staying up so late.
Yeah, okay.
Thank you. Bye bye. 谢谢.
Thank you. Thank you. Thank you. Okay, bye.
Bye.
Bye bye.
We'll move into our second speaker. Our second speaker is Professor Eike Mueller. Yeah, I see him. Okay. So, hello. We would hear from him about exact conservation laws for neural network integrators of dynamical systems. And he's an associate professor for scientific computing in the Department of Mathematical Sciences at the University of Bath. Originally trained as a physicist, Eike works on development and implementation of efficient numerical algorithms to tackle challenging problems in science and engineering. His work has led to the significant impact by improving the performance of UK's operational climate and weather forecast model. Recently, he has been working on the application of machine learning methods for the solution of partial differential equations, with the particular focus in incorporating physical knowledge into the neural network architecture. Before joining the University of Bath as a postdoc in 2011, he completed his PhD in computational particle physics in Edinburgh and worked as a scientist in UK Meteorological Office from 2009 to 2011. With that, we would want to welcome you and let's hear from him. Thank you.
Okay, yeah, thank you very much for the kind introduction and for the invitation. So it's not that late here, it's just turning dark and it's raining. So all the work on the weather forecast model didn't help with this. I guess I should start and share my screen. Let's see. Does that work?
Yes, it works. Yeah.
Okay, perfect. Yeah, so this is some work on trying to incorporate conservation laws into neural network integrators for dynamical systems. So here's an overview of my talk. So how much time do I have? Sort of 45 minutes plus questions, is that right?
Yes, we are pretty flexible with time. 45
okay,
to 50, 55 minutes, yeah.
Okay, perfect. So I just want to give some background and motivation onto why I've been looking at that. And then in the core part of my talk, talk about the techniques for incorporating these conservation laws into the architecture of neural networks. And there's kind of two kind of key ideas. So one of them is Lagrangian neural networks, and which is a very recent idea. And then the other idea is about 100 years old, and that's Noether's theorem. And putting this together will allow us to build kind of symmetries into neural networks. And then I'm going to show some results. So one is about the motion of a particle in the Schwarzschild metric, and the other one is about the simulation of two interacting particles. So there you have a bit more symmetry. So there's translational symmetry involved in rotational symmetry. And at the end, I want to give a summary and outlook. Okay, so what's the key problem or the challenge that we're looking at? So really what we want to do is we want to predict the acceleration of a particle from its position and velocity. So we want to learn the dynamics of a dynamical system from data. So assume that the true dynamics is given by this black curve here. So at every point in time, we have some position, some velocity, and then some resulting acceleration. And we want to predict the relationship between these quantities here. But the only thing we have is some data. So we have some data, and that data can be noisy. So because there's some measurement error or whatever. So one system you can think about is kind of planetary motion. So when Kepler tried to derive his kind of laws of the solar system, he looked at the stars and he measured their position and their velocity. He probably wasn't really able to measure the acceleration directly, but he could somehow infer it. So that's kind of the thing of this the type of problem we're looking at. So we want to learn this function phi here. And then obviously the first thing you can do is you can try to train a neural network, which takes in position and velocity. And then it tries to somehow predict the acceleration. And that's just a complicated function. And you minimize that. So you train that neural network by minimizing some loss, which compares the measured acceleration to the predicted acceleration. So there's a bit more to this motion usually. So there usually are physical constraints. For example, conservation laws. So we know, for example, that energy is conserved. In many cases, there might be other quantities that are conserved, like the linear momentum or the angular momentum. And for some physical system, this is really, really crucial. If you have this spinning top here, then conserving angular momentum is really important because that stops it from falling over, for example. So the neural network doesn't know anything about these constraints, so it somehow has to discover them from data. And even if it somehow learns them, the conservation laws it will learn are only kind of approximate. So that's the best it can do if we take this naive approach. So you can try to improve this. So you can, for example, try to build some soft constraints into loss functions. So you can penalize any deviation of the angular momentum at a later time from the initial angular momentum. So that's what I tried to write down here. And there's different ways of doing this, but even if you do this, the conservation is still only approximate. So the key question that I want to try to address in this talk is really as to whether we can build the conservation law somehow in the neural network, into the neural network, and kind of do better than this. And the answer is we can do this. So we need two ingredients. So we need to look at Lagrangian neural networks, which were proposed very recently. And then the other ingredient is Noether's theorem. So now I should, of course, say there is other work in this direction. So there is generic structure preserving neural networks, which sort of can, in a sense, be seen as looking at more general problems. So there you are looking at non-equilibrium thermodynamics. And I think if you leave out this term here, then you essentially recover Hamiltonian dynamics. So that's kind of similar to the setup that I'm looking at here. So there are symplectic recurrent neural networks which try to conserve one quantity. So they try to conserve energy, and they do this essentially by constructing a shadow Hamiltonian, which is exactly conserved, and that then leads to the approximate conservation of energy. And the idea here is that you split up the Hamiltonian of the system into a kinetic part, kinetic energy, which depends on position, and the kinetic energy, a potential energy that depends on position, and a kinetic energy that depends on momentum. And then if you use, if you represent these two bits by neural networks, and then you use a symplectic integrator like Leapfrog, then you can conserve some shadow Hamiltonian, and then the energy is approximately conserved. There's some other work trying to incorporate conservation in neural networks. So there is, for example, some work on mass conservation in photochemistry, and there's probably lots of there's other stuff that I'm not mentioning here. This is a growing field, of course. Okay, so let me now come to the main ideas. And the first thing I want to talk about is this idea of a Lagrangian neural network. So this is from this paper from 2020. And the idea here is that instead of learning this function phi, which takes in position and momentum or velocity and gives us the acceleration directly, we learn the Lagrangian of the system. So the Lagrangian is a function of the coordinates in phase space. And from this Lagrangian, we can derive the equations of motion using these laws here. So that's minimizing some action. And that is, in a sense, you can derive Newton's laws in this way. Okay, so and if you take these equations here and then take another time derivative, you get an expression for the acceleration. So you can solve this for the acceleration, and you get this expression here. If we now represent the Lagrangian by a neural network, so the L takes in some Q and Q dot, and plug it into this formula, we get the acceleration. And of course, TensorFlow or other frameworks, they can do this here very efficiently. So we sort of get this representation of the function phi that we're looking for. Okay, so the advantage of this is, of course, that we can then use the entire machinery from analytical mechanics in this context. And one important theorem in this framework is this theorem that was formulated by Noether in 1918. And in a nutshell, this theorem says that whenever the Lagrangian has a continuous symmetry, then this leads to a conservation law. So that means that there is a certain quantity, physical quantity, that is conserved. So here are some examples. So if you have invariance under translation, so if we take our physical system and we can shift it without changing the dynamics of the system, then momentum is conserved. And if we have a system which is invariant under rotations, so we take the system and rotate it, and the physics doesn't change, then angular momentum is conserved. So in one system that has this property is the solar system. So if we just take the sun at the origin of the solar system and then look at the motion of planets around the sun, then this is a rotationally invariant system. So if we rotate the entire thing around the sun, then the physics will be exactly the same. And the reason is, of course, that the force between the sun and the planets is a central force, so it doesn't change under rotations. And then this rotation invariance implies the conservation of three-dimensional angular momentum. And that has consequences such that the planets all move in a plane, and that the area that they sort of cover in a given time interval is constant. So they move faster close to the sun and slower further away from the sun. So that's one very famous example. And then there's more applications. So if you think about field theories, for example, then these theories, they can have so-called gauge symmetries. And then these gauge symmetries lead to properties like charge conservation, and these symmetries play an incredibly important role in modern physics, like particle physics. Okay, so here's the theorem in more mathematical detail. So what we assume that the Lagrangian of the system is somehow formulated on a manifold with a tangent bundle, and the Lagrangian is a function from this tangent bundle into the real numbers. So this simply says that it takes as input the position and the momentum, and it gives us some real number. So that's the Lagrangian. And for this talk, I'm not looking at constraints. So you can always think of the manifold as just a d-dimensional space, and the tangent bundle is also d-dimensional space. So yeah, in this case, this is actually quite straightforward. So we have this Lagrangian, and then we assume that we have a family of maps. So this family of maps HS is parameterized by a continuous parameter S. And we can then compute the local derivative of this map at any point Q. This maps from the tangent space at the point to the tangent space at the mapped point. And again, in Rn, this is just sort of the normal derivative of this map. So it's nothing mysterious. So and what we assume now is we assume that the Lagrangian is invariant under these transformations. So that means that if we transform the coordinates with HS, and we transform the momenta which live in the tangent space with H star or the velocities, then this gives the same result as the original Lagrangian. So the transformation doesn't change the Lagrangian. So that's the assumption. So that means that the Lagrangian is invariant, and Noether's theorem now says that if this is the case, then there is an invariant quantity, and we can work out what that quantity is by taking an appropriate derivative of the Lagrangian and the derivative of this map at s equals 0. And this quantity I here is then a constant of motion, in the sense that this doesn't change over time. So this stays the same during the motion, so it doesn't change. Okay, so just to give you one example, if we have a particle moving in three-dimensional space, then and there's no constraints, then the position and the velocity just live in the product space Rn cross R3 cross R3. So that's our tangent manifold in this case. And if we assume that the physics is invariant under rotations, so we assume that if we rotate both the position and the velocity with some rotation matrix R, then the Lagrangian doesn't change. So the R is just an element of the group of rotations, so SO3. So the R times the R, sorry, R transpose times R is just the identity matrix. So this is kind of the symmetry group in this case, and the maps can be written as HS, which is R times Q, and HS star of V, which is again R times V. So we rotate both the position and the velocity, and the R can be written as this exponential of an element in the Lie algebra of this group here. So the gamma is a linear combination of these matrices here. So that's the symmetry group. So these rotations of both position and velocity leave our Lagrangian invariant. So that's the assumption I make. And I can then work out the conserved quantity. And the conserved quantity in this case is something like a generalized angular momentum. So we have the derivative of this map here, and we can work this out. So this is just gamma times our position, where the position is a linear combination of these antisymmetric matrices, and then we multiply it by the derivative of the Lagrangian with respect to the velocity. Okay, and in 3 dimensions, you can now work this out. If you plug in the expressions for the matrices from the Lie algebra, you get these 3 conserved quantities here. So they look like this. And if we then assume that the Lagrangian isn't just arbitrary, but is actually describing the motion of a particle in a central potential, so the V only depends on the distance from the origin, and the kinetic term looks like this, then we can work out what this derivative here is. And the dl by d qj dot just gives us the qj dot times the mass. And in this case, this expression reduces to the normal angular momentum. So that's what you can find in your physics textbook. So, but note that if I have an arbitrary Lagrangian here, and I assume it's invariant under this transformation, then these quantities Lx, Ly, and Lz, they are still conserved, even if the Lagrangian doesn't have this very specific form where I split it up into this kinetic term and the central force potential here. Okay, so now the central idea really is of this talk is really very simple. So if we want to learn the dynamics of a system that has a conserved quantity, what we do is we simply construct a neural network Lagrangian that is invariant under the corresponding symmetry transformation. So if we want to conserve angular momentum, sort of the physical angular momentum that we have here, we will not recover this exactly because that assumes that the Lagrangian has a particular form, but we will at least kind of recover something which looks very similar. So this is a bit like the shadow Hamiltonian that is kind of conserved in symplectic integrators. Okay, so how do we do this? So we want to construct a neural network Lagrangian that is invariant under our symmetry transformation, and there could be several symmetry transformations. So all we do is we take we just kind of add an additional layer. So that layer takes as input Q and Q dot, and it just spits out all scalar quantities that are invariant under the symmetry transformation. So that's a so-called symmetry enforcing layer. So that takes in this Q and Q dot, and it spits out some Sj, which depend on these two variables. The only condition is that if we change the inputs here in this way, then the output of this layer doesn't change. And that idea is actually very similar to what people do in physics when they construct new theories. Sort of in particle physics, people do this very often. So they just say, okay, we have a system, we know what its symmetries are. So let's now just write down all the terms that are invariant under these symmetries. And then we don't know what the coefficients of these terms are, but we can sort of infer these coefficients from data. And the idea here is very similar. We kind of do the same. We construct all invariant scalars, but we then feed them to a neural network, and that gives us our Lagrangian here. And once we have the Lagrangian, we can derive the equations of motion just by taking the appropriate derivatives. Okay, so let's have a look at an example. So if we go back.
Hi, Professor Mueller, there's a question around which I can barely hear.
Sorry, can you hear me okay?
You're very faint.
Very faint. Here, I'll just speak really close to the microphone. So are you assuming a priori that you know the invariance that you're trying to impose, or is that something you're attempting to discover?
I only assume that I know the symmetry.
But like in terms of a gauge symmetry or something like that, it could be very complicated. So so is this more about just imposing like translational and rotational symmetries? Is that what you have in mind?
Yeah, that's what I've looked at so far. Yes.
I see. Okay, thank you.
Yeah, but it would be very interesting to look at more complicated symmetries, of course. Yes. Yeah.
Okay. This was Nat Trask from Sandia. He forgot to introduce himself. He's another one of these structure preserving guys.
Mm-hmm.
So he has one of the papers, I think, that you mentioned.
Yeah. Mm-hmm. Okay, so the examples, the symmetries I'm looking at here is really rotation invariance and translation invariance. That's the only ones I looked at so far. Yeah. Okay, so but let's have a look at the rotation invariance. So in this case, so we're in R3 again, and we're just looking at these rotations. So I rotate Q and Q dot. And now the question is, what are the invariants I can construct from these two vectors? And there's only really three. So it's Q squared, Q dot squared, and Q times Q dot. Okay, so that's the three invariants I can have. So what I do then in my neural network is I take Q and Q dot, I construct these invariants. So that's kind of this layer S here. And then I just add some dense layers. So there's just L dense layers. And that's it in this case. So here's the full network. So again, I put in the quantities. I have my symmetry enforcing layer. I get invariance.
Excuse me, can I ask a question? This is Panos Tinis from Pacific Northwest National Lab. You said that this reminds you of what people do in high energy physics, right? So in high energy physics, if you write down the terms that you can get from symmetry, then to put the Lagrangian together, you just sum them up with,
Yes.
you take a linear combination of them. So why do you need the dense layer then here, which is nonlinear? Why don't just take a linear combination of scalar invariants?
Well, I mean, in this case, this wouldn't be enough, right? I mean, if you have a quartic potential, then you would need Q squared, right?
Okay, so in other words, it's more complicated than what you do when you just put the terms together that come from symmetry.
Yeah. Yes.
Yeah.
I mean, yes, I need to do more.
Otherwise, you wouldn't need the dense layer, right? You could do just
Yeah.
a linear combination and it would
Yes.
work. But this is not enough in your case. Okay.
No, it's not enough. No.
All right.
Yeah.
Thank you.
Yeah. Okay. Yeah. So this is the network again. So I construct the invariants. I pipe them through my dense layer, so I get the Lagrangian, and then I take derivatives, which is done by TensorFlow, and I get my output. And that's really it. So the only thing I did is I just added this additional symmetry enforcing layer. Okay, so let's have a look at some results. So for the network,
sorry to interrupt you again. Hopefully you can hear me better. I think I must be missing something because I don't understand what is going on in that red box that enforces the symmetry. Can you speak to that?
Yeah, I mean, that's really just what I described here. So I take my input Q and Q dot, and I construct scalar invariants. That's all.
So this is basically feature engineering. You're forcing it into a representation which respects those invariances. Is that the idea behind it?
Yeah, I guess that's how you could call it. Yeah.
I see. Okay, thank you.
Yeah, I'm also sorry. I'm also a bit curious on this question. Maybe you explain. So, what is for the R here? Is that learned from the neural network, or is that given? I mean, this kind of orthogonal matrix.
This is a given. I assume. I mean, I never need that in my network. I'm just assuming invariance under rotations.
Oh, I see. So you don't really need this R.
No.
I see. Okay, cool. Yeah, thank you.
This could be something else. I mean, I could have, I don't know, I could have some other Lie group, for example. I mean, then obviously the invariance would change, but that would be possible. Yeah.
I see. Yeah, thank you.
Excuse me, a follow-up question to Nat's question. So if the symmetry layer doesn't do anything else than compute the S1, S2, and S3, then have you checked that the Lagrangian that you get, the L and N, actually conserves this that these quantities that you get from this Lagrangian that you learn are actually conserved?
Yes, that's what I'm going to talk about next.
Okay.
Yeah.
Because you don't actually enforce the symmetry in the symmetry layer. You just, like Nat said, you do feature engineering. I mean, very well chosen features because these are these scalar invariants. But then, all right. Thanks.
But by construction, my Lagrangian will be invariant under these symmetry transformations.
Right. That's what I want to see.
Yeah, and that's what I checked. Yeah.
Okay.
Yeah. Okay. Yeah. But very valid point, because obviously that was one of the first things I checked in my code. Because if it violates that, then there's a bug. So yeah.
Another related question: the input is also Q and Q dot. Why do you need S, kind of the neural network, to have Q squared and Q dot squared? What am I missing there?
No, the input is Q and Q dot, and the output is Q squared, Q dot squared, and Q dot. This is just
why
one
do you
layer.
need the network, the S in between?
Oh, so yeah, I mean okay, so that's maybe a bit confusing. So it's not really a network. It's literally just a layer. It's literally just taking Q and Q dot and returning 3 other scalars. So it's
I see. Okay,
it's very simple. Yeah, there's nothing complicated going on there.
Thanks.
Okay, so yeah, let's have a look at some results. And one key question for me was actually, does it preserve these quantities? So, but I come to that. Okay, so just a few words about the network architecture. So for the dense layers, I just used 2 layers with 128 nodes each. So for the activation function, I used soft plus. I didn't do anything fancy like batch normalization, and I didn't try to optimize the architecture or tune hyperparameters. So that was just done on my single GPU. So I haven't really looked at that. And all computations are done in single precision. So that's something I should stress, because that obviously has an impact on the relative errors. So if you do single precision arithmetic, you expect something at the order of 10 to the minus 7. And that's something we also see. So there is some TensorFlow code if you want to have a look at that, play around with this. Okay, so a few words on training. So to train these networks, I fixed the initial condition, and then I integrated 2 trajectories with an RK4 integrator. So I assume that I know the true Lagrangian for my system. But obviously the network doesn't know it, the network wants to learn it, but to generate training data, I know it. So I use an RK4 integrator, so that should bring the integration error down to kind of a level that's kind of about rounding error. And then I just sample these trajectories at some given times, and I add some normal random noise, and the strength of the noise is 10 to the minus 3. And I train the networks over 250 epochs with 100 steps per epoch and a batch size of 128. So that's just what I did. And I'll show you a loss function in a minute, but as the loss, I just minimize the mean square error. So I just take the predicted acceleration, which includes the error, and I compare it to the neural network prediction, and the neural network only sees the noisy data. So these are the noisy inputs, and I just want to minimize this loss. So I want to get this mismatch as small as I can, but obviously there's a lower bound. So because I added this noise, so this here is bounded from below by 10 to the minus 6. Okay, so here are some loss histories. So for the first model problem, so that's this motion in the Schwarzschild metric. You actually, this is very small, but actually the loss goes down to 10 to the minus 6 relatively quickly, and then it stays there. So it can't go below the noise level. So the second model problem is more complicated. So I have 2 interacting particles in 4 dimensions. So there the loss goes down to just below 10 to the minus 4. So it is possible that, I mean, either the network is not, I'm sort of underfitting and the network is not sophisticated enough, or I need more training, but that's kind of the point that I got to. Okay, so let me say a few words about the model problems. So the first one is the motion of a massive relativistic particle in the Schwarzschild metric. So that's kind of the motion of a particle around a black hole without angular momentum. So this is a picture from this movie. I think the black hole in the movie actually had angular momentum. But anyway, so the true Lagrangian can be written like this. So it depends on position. So that's a 3-dimensional vector. Velocity, which is also 3-dimensional, and then it's kind of a relativistic motion. So I have a time coordinate, tau as well, which is, I believe, the time measured by an observer who's infinitely far away. So that's a true Lagrangian, which looks like this. And what I'm trying to do is I'm trying to represent this by a neural network Lagrangian. And if I don't put any constraints on this, then I assume that it just depends on the position, the velocity, and the derivative of this time here. So that's kind of the benchmark that I compare this to. So I didn't try to build any symmetries into the system. And then I replaced this by a neural network which is invariant under these symmetries. So in that neural network has this symmetry enforcing layer. So essentially, this neural network only depends on these scalar invariants here. Okay, so and even though you might not really see this from this Lagrangian here, so the Lagrangian is actually invariant under rotations. So it preserves angular momentum, which is just this quantity here. And the neural network, so this neural network here, the rotationally invariant neural network, will also preserve angular momentum, but it's not quite the same. I mean, it's kind of the position crossed with the derivative of the Lagrangian with x dot. So that's what the network will preserve exactly, and it will preserve this up to rounding errors, and that's something I will show you in a minute. Okay, so here are some results. So what I show here are trajectories generated by the two neural networks. So the first one uses the unconstrained Lagrangian, so that's shown at the top, and the second one uses this rotationally invariant Lagrangian. So and what you see here, so red are the true trajectories. So it's kind of going around the black hole, and it's kind of it's not going in an ellipse. It's going kind of the orientation of the ellipse is rotating. So but anyway, so for the unconstrained neural network, you see that the trajectories don't really resemble the true trajectories at all. So they're very different. So that's kind of a view from the top. If you look at it from the side, they don't lie in a plane. So that's kind of the key takeaway. So the neural network certainly doesn't conserve angular momentum very well. I mean, it tries to do it. I mean, it's learning it from data, but it's kind of oscillating around the plane. So and that problem goes away almost completely for the rotationally invariant neural network. So you can't even see the true trajectory because it's kind of covered by the predicted one. And actually what I simulated is both a neural network trajectory and then the same trajectory, but with a perturbed initial condition. So and the other thing you see here is that this kind of trajectory with a perturbed initial condition stays very close to the unperturbed trajectory. So that's another nice property of this system here, and that goes away for the unconstrained neural network. So and for the rotational invariant neural network, the motion lies in a plane. So okay, so can we make this a bit more kind of can we make this a bit more rigorous? So so the trajectories look nice, but do they actually conserve the quantities I want them to preserve? So to measure this, I computed the true angular momentum. So that's the one that I would get from the true Lagrangian. And I computed the so-called neural network angular momentum. So that's this quantity here. And then I looked at the time evolution of these quantities. So I measured them at a given time t, and I compared it to the initial time, and I divided by the initial value of the quantity, just as a normalization. Okay, so what I show here is this deviation. So that's a logarithmic scale as a function of time. So time is shown on this axis here. And in red, I always show the one, this neural network quantity here. And the dotted, so dashed blue curve is the true quantity. So the unconstrained neural network is sort of trying to learn the conservation of angular momentum, but it's not doing a very good job. So the error is, the relative error is about 10%. So and it's not getting better than that. And if you look at the neural network that has this rotational invariance built in, then this looks very different. So if we look at the neural network quantity, so that's the red curve, then this goes up to 10 to the minus 5. But that's just rounding errors. I mean, they accumulate, and I reran the simulation in double precision, and the error gets reduced to yeah, as you would expect, to rounding error in double precision. So that's kind of showing that, as I expect, the neural network really conserves this quantity here, up to rounding errors, of course. So that's nice, but really we want to conserve this quantity here. And if you look at the curve here, you see that the true angular momentum is also conserved much better. So the error is 10 to the minus 3, and it doesn't really go above that. Okay, so then the final thing I looked at is stability under perturbations of the initial conditions. So what I plot here is the kind of deviation of the unperturbed and the perturbed trajectory as a function of time. And the initial perturbation is 10 to the minus 3. And what you see is that for the unconstrained neural network, this grows and it becomes larger than 1 after a certain time. And for the rotationally invariant neural network, this growth is much weaker. So you deviate by much less as time increases. Okay, so this was the first model problem. So the second model problem is a bit more complicated, but the idea is the same. So I have two particles moving in d dimensions now. So they have some positions, x1 and x2. And I assume that the true interaction potential has this form here. It's sort of a double well potential, so it only depends on distance. And I can write down the true Lagrangian, which consists of kinetic terms and a potential term here. So that's kind of the true Lagrangian. And I can now look at the symmetry properties of the system. Because the potential only depends on the distance between the two particles, the whole system is invariant under translations. So if I shift the positions by the same vector, so I take the system and I shift it, the physics doesn't change. So that's kind of the first symmetry of the system. But then there's another symmetry because the force between the two particles is also only acting in the radial direction. I can also rotate the system, and that doesn't change the physics either. So I have kind of invariance under this group SOD. You can write down the Lie algebra, and you can write down the fundamental representation for this, and that gives you these matrices here. So the symmetry structure is a bit more kind of rich than for this simplified problem that I looked at before. Sorry, for this motion in the Schwarzschild potential that I looked at before, where I only had this three-dimensional rotational symmetry. Okay, so now the question is, if I have these symmetries, what are the invariants that I need to construct in the symmetry enforcing layer? So what are the invariants that I need to feed to the dense layers of the neural network? So for translation invariance, this is relatively straightforward. So we know that everything can only depend on the relative distance. So all we have to do is we have to replace x1 and x2 by their difference. So, and if we do that, then any shifts here will not change these quantities, because any shift in x1 is compensated by the corresponding shift in x2, and shifts don't have any impact on velocities. So rotation invariance is a bit more complicated in d dimensions. And there is some notation that's introduced here. So if I have n vectors, so A1 to AN are vectors in d-dimensional space, then the set of scalar invariants is simply given by the set of all possible contractions of these vectors here with either the metric tensor or with this Levi-Civita symbol. So that's just a set I construct somehow, and you can write this down. It's in 3 dimensions. For example, if you have 3 vectors in 3 dimensions, then you can, for example, form scalar products, but you can also form kind of an area. So you kind of take the cross product of 2 vectors and you multiply with another vector, and that gives you a volume, and that volume is also invariant under rotations. Okay, so that's really all I do. So I take my inputs. I first construct this quantity here, and then I construct all possible contractions, and that's then my sort of symmetry enforcing layer. So I reduce it to these features, if you want to call it like that. Okay, so what are the conserved quantities? So translational invariance gives us linear momentum conservation, and for the neural network, we conserve this blue quantity here. And there's actually d components, so this is a vector with d components. And then for the true system, we know what this is, so we can work out these derivatives, and we get these quantities here, which is just, I mean, that's just the sum of the momenta of the two particles. And for the rotational invariance, we get angular momentum conservation. So we just work out these generalized angular momenta for the two particles. So that's particle 1, that's particle 2, and we add them up. And then for the true Lagrangian, we get these quantities here. And there is d times d minus 1 over 2 of these, and they just come from the number of generators in the Lie algebra. Okay, so here are some results. So what I did is I simulated this system in 4 dimensions, and I mean, these are just projections. So the two particles are shown in blue and red, and the true trajectories are shown as these dashed lines here, and then the predicted ones are shown in as solid lines here. So and what I did is I first started with a completely unconstrained neural network. So that's shown up in the upper left corner. And then I switched on the symmetry. So I first constructed something which is only translationally invariant. So that's the first entry in the bottom row. And I also constructed something which is only rotationally invariant in the top row here. And then finally, I built all the symmetries into the system. And that's what I get at the bottom right corner here. So and if you look at this, I mean, just looking at the trajectories for the unconstrained network, they look wrong because the particle is kind of going back on itself here. So that's not really what's happening in the true system. And it gets better as we switch on the symmetry enforcing layers. And the best trajectories are really the ones where I enforce both symmetries. I mean, I'm still off, but it's looking much better. Okay, and then I looked again at the conserved quantities. So again, there's 4 plots. So I start with the unconstrained one, and I go to the one where I constrain, where I build in both symmetries. And again, I look at both the quantities defined for the neural network and the true ones. And what we can see is if we look at the unconstrained ones, so that doesn't really preserve the true angular and linear momentum really well. So there's sort of errors which go up to like 10 to 100%. So that's the dashed curves here. And if I switch on the symmetry enforcing layers, then conservation is better. I get kind of errors of only just around 1%, and they don't really grow. And then as expected, sort of the neural network invariants, they are kind of conserved up to machine precision. So that's, yeah, I'm almost at the end. So the final thing I did is I looked at stability under perturbations. So again, I initialize the network, and then I look at the slightly perturbed trajectory, and I measure how they kind of diverge. And for the totally unconstrained neural network, they diverge quite a lot. So that's consistent with the trajectories I showed you on the previous slides. And then switching on the symmetries actually helps with this. So interestingly, the translation invariance seems to help almost as much as switching on both translation and rotation invariance. Okay, so that brings me to my conclusions. So that shouldn't be future work, that should be just a conclusion. So I talked about neural networks with built-in symmetries, and I used this combination of Lagrangian neural networks and Noether's theorem to build exact conservation laws into the networks. And I also showed that that leads to improved stability under perturbations of the initial conditions, which is, of course, a property that you always want when you train these networks to simulate dynamics. So yeah, I think there is lots of kind of potential for future work. So I only looked at point particles. It would be interesting to look at continuous systems. So I think in the Lagrangian neural network paper, they look at that as well. They start looking at some wave equations. Would be interesting to look at other symmetries, so other Lie groups, symmetries of these continuous systems. So the other thing I haven't really looked at is symplectic integrators. So I haven't looked at energy conservation here. So that's something that you might want to do. So you might want to look at this whole stuff in a Hamiltonian framework where you can preserve energy as well. Yeah. So there's a preprint and there's some code if you want to look at the details. Yeah, just look at these. So yeah, that's it.
Thank you, Ike. I guess Nat has more questions probably.
I have a question. Thanks for your talk. I have a little question. You add a Gauss noise to the date. This noise attenuates very fast. But if you add another kind of noise, such as Levy noise to a date, can this method be similar performance?
Yeah.
That I mean.
Yeah. That's a good question. I haven't tried this. I have to admit the noise level is relatively low that I added, so just 10 to the -3. So it would be interesting to see what happens if I increase this. It would also be interesting to see what happens if you can't observe the entire state, if you only can sort of observe projections. Like when Kepler looked at the planets, he didn't see the radial motion, he only saw the motion in one direction.
Okay. Okay, thank you.
Yeah, I have one question, maybe more open-ended, and it's related to the idea of the actual gauge symmetries. So these ones you can work out through clever choice of feature, but those are things related a lot more to like the algebraic structure, like the divergence of the curl is equal to 0 and exact sequence properties and stuff. Do you have any ideas about how, like, is that something you're interested in? Have you thought about how to go after those more complicated structures?
Yeah, so it's definitely interesting. I haven't looked at that, but I know there is people who look at, they are more interested in Monte Carlo simulations, which is obviously a big thing in these gauge, so for these gauge theories like lattice QCD. And they actually, they're interested in sampling from the distribution, which is obviously a very different approach. And they build these symmetries into their networks. So they actually make sure that these symmetries are observed. So obviously now the additional complication there is that you have local gauge symmetries. So I've only talked about global symmetries here.
Great talk. Thank you.
Thanks.
Hi. Hi, Ike. Can I ask a question?
Yeah, sure.
This is Jen.
Jen, please identify yourself so the speaker would know who you are.
Yeah. So this is Jen. I'm a 5th-year graduate student at Brown in the Crunch group. And so thanks for the very nice talk. I'm curious about because you talk a lot about this kind of symmetry preserving Lagrangian neural network. So I'm wondering whether it can be applied to, for example, optimal control problems, because you also have Lagrangian and you want to preserve symmetries in that sense. I'm wondering, is that applicable, and have you thought about that?
I haven't thought about this, I have to say. But yeah, would be interesting. Yes, definitely.
Okay. Yeah. Okay.
He's talking about drones and optimizing trajectories and so on. Jen has a paper with
Okay.
colleague who does optimal control, and that could be probably applied. Yeah.
Mm-hmm.
Can I ask another question? Quick question.
Sure. Yeah.
Yeah. So I don't understand how are symmetries built in the sense, can you actually take the output and use it to compute these capital I, which are the invariants, and take the derivatives with respect to time and show on paper that it is 0?
Yeah, I can show this. I mean, so, well, it depends on what I you mean. So, I mean, for example,
I mean,
here,
this capital M, it's capital M, yes.
yeah, the M with the subscript NN, I can show on a piece of paper that it is conserved.
Okay.
Yeah.
Okay.
That's just follows from Noether's theorem.
But what I don't see is why something that gets differentiated through an arbitrary dense layer would still conserve capital M. That I don't understand that.
Yeah, no, I think the argument is simply, so Noether's theorem tells us if we have a Lagrangian, and that Lagrangian is invariant under the symmetry transformations, then these quantities are conserved.
Okay, but by making the Lagrangian a function of the invariance, I don't see why the Lagrangian is preserved. That's what I don't see.
So yeah, okay, there's two invariants I think we're talking about here. So one is this M here, for example, or the L.
Right.
Yeah. So that's kind of
that comes then from Noether's theorem, but but I don't understand why the L that you construct, which takes as an input these scalar quantities, is actually invariant under transformations.
Okay, so the thing that's invariant is the thing which takes Q and Q dot as an input.
Right.
Okay, so it takes Q and Q dot. The Q and Q dot are reduced to these invariant quantities.
Right.
And I know that they don't change. So I have S1, S2, and S3, and I know that they don't change if I change the Q and Q dot according to the symmetries, right?
Okay.
And now I take these now I have a function of quantities that don't change if I apply the symmetry. So therefore the function must be
I see
invariant.
Okay.
And that's all. And that's all I need. And then I can apply Noether's theorem. And that gives me that. I mean, it doesn't tell me that the true quantities are conserved. I don't get that. But I get that these are conserved. And this is a bit like a shadow Hamiltonian, right? So I know that the shadow Hamiltonian is conserved. And this kind of usually means that the energy is kind of not exactly conserved, but it's kind of, for example, it doesn't drift.
But if you know that the system somehow should conserve the true quantity, why that is also a bit a mystery. Why is it not conserved exactly like the other quantity that you can actually show that it is conserved?
Yeah, because I mean, this quantity here is only conserved if the L has a particular form. I
see.
Yeah.
It has to be the exact.
Yeah.
I see.
Maybe not exact, but I mean, so for example, in this case, I could have a different potential. So the potential could be different,
right?
But I have to make sure that if I take these derivatives here, I kind of recover.
I see.
And I think there's a mistake. This should be Q1 alpha dot and Q2 alpha dot.
Okay, so these are the generalized somehow momenta that are conserved, like the example that you showed. And if then you have a central potential, then you go down to the okay. Yeah. All right. Thank you.
Yeah.
Very nice talk. Thank you.
Thanks.
Mia, Kirkus, do you have a question? I'm asking.
Hi, hello.
representative of a structure preserving the Spanish paper.
Yes, I'm Kerkus Hernandez. I'm an intern at Brown, and I'm one of the authors that you first mentioned about structure preserving things. And now I just have a curiosity. Why did you choose the Lagrangian formalism against the Hamiltonian formalism? It's just a curiosity, because in the Hamiltonian you have doubled equations but lower the order, so it makes more stable integrators, and I think it has more expressivity in the neural network sense. So it's just a curiosity.
Yeah. Okay. So I mean, the argument they give in the Lagrangian neural network paper is that you don't rely on specific coordinates. I mean, you need canonical coordinates to use the Hamiltonian approach, right? And and I think also Noether's theorem is formulated in terms of the Lagrangian. So I would need to think about how you reformulate it in terms of the Hamiltonian. It's probably pretty trivial, but I haven't thought about it. Yeah.
Okay. There are several papers in the formalism that I use, the generic, which is a more general form of the Hamiltonian, has a kind of method to include an arbitrary invariant. So in the degeneracy conditions, but well, that's, I guess it's future work.
and that's exactly conserved.
No, it will be a soft constraint. Yes.
Right.
So that yeah, maybe you should think about one trick like that just to conserve it hardly. Yes.
Yeah. So I mean, I think one thing I could do here is I could, of course, in addition, I could put a soft constraint on the true quantities, right? I mean, that sort of can't hurt, and that might improve it even more. Yeah.
That can seal the deal.
Yeah.
Okay. Thank you very much.
Great talk, Eike.
Thanks.
So
I think Zen has some more questions. Probably he just unmuted the mic.
No, I was just trying to like comment that in Poisson formalism or generic formalism that we don't require like canonical coordinates, but I think Kerkus already mentioned that. So yeah.
Okay.
Eike, do you know that paper? We have a paper on Poisson. Actually, Jen's paper is on Poisson. What do you call it? The Poisson neural network.
Yeah. Poisson neural network.
Yeah, I tried to look at the three papers that I cited here, and I mean, I have to say this generic formalism is something I still need to get my head around. So it's
no, the Poisson is a different one. It uses it for non-canonical. It extends the Hamiltonian to non-canonical coordinate transforms. Non-canonical coordinates. Yeah.
So that's another paper. That's a different.
That's another paper. Yeah, I did.
Okay.
Yeah,
okay.
in the text, I just just give you a flavor of basically what people are around me and elsewhere around the world are doing. So I was just trying to excite your imagination, because I thought you did all this work kind of in an isolation on your own, but there are other people who also have. So I thought you.
Sure. Yeah. Yes. I mean, I know there's a lot out there, and I'm sorry that I didn't cite.
No,
the literature.
No problem with the citation. It's just so that you are aware of all these other efforts.
Are there more questions?
Hi, this is Eson from Carbon. I have more like a comment, not a question. It was interesting, some thoughts to think about, but for example, in solid mechanics, in continuous systems, rigid body rotation, we know that should not cause any stresses or any strains, because and the kind of approximations should be rigid body invariant. Yeah, ever since you started describing your approaches, I'm thinking how I can incorporate that into the neural network. There are some rules, like you can go from if you take an infinitesimal vector deformation gradient, give you the mapping from initial coordinate to the deformed coordinates, and how that can be incorporated into the network. Yeah, it's more like a comment, but it was interesting. I want to thank you.
Yeah, there's a paper where they looked at sort of turbulence modeling for fluid dynamics. And in that context, what people have done for a long time, they essentially wrote down invariants, and then they used these to somehow construct phenomenological models.
Yeah, that's JFM paper by Julia Ling. Yeah,
exactly. Yeah, exactly. And so I don't know if that's applicable in this case.
Yeah, in finite element too, like lots of work, but in neural network, I need to think about it, but it's like a standard implementation. If we just implied rigid body rotation to the system, it would cause some error in terms of displacement. It's not going to be exactly zero. So interesting. Yeah, thank you.
Thanks. Yeah.
Some data. Did you tell the speakers that they will be on YouTube?
No, I haven't. I was about to announce that. Yeah.
Okay.
So I would be uploading the seminar today on YouTube, and I would send you a link. Maybe you would want to subscribe to our channel. It's Crunch Group on YouTube.
Okay.
It's free. We have to say it's free. When you subscribe, it's free for free.
Okay.
She's not very good in selling her stuff. I can.
So thank you everyone for tuning in today, and have a great weekend and have a great rest of the day.
Yeah.
Hey, thanks a lot again for the invitation.
Bye.
Yeah.
See you. Bye.
Thanks. Bye.